Good day to you. This is Anagalactic, bringing you another scientific presentation on the first day of winter. My usual video a day, always trying to add content. We're discovering the dynamic system of the universe. You don't understand Maxwell's equations. Let me repeat the title of this video. This is a 15.5-minute video. Very well done, I think. Ali al-Karaguli. Now, in dealing with equations, Ali will show us the four Maxwell equations, and you can see he's drawn a big pink X through all of the divergence equations because he's going to show us a better way to understand. This is always an invitation. But Ali is a handsome man. He's an intelligent man. It's obvious that he has a good heart. I am a very quick study. I have to be. So we're going to follow what Ali is saying here. I'll be making some comments along the way. My document is in production now. It will be produced at a GitHub site. If you wish to click on that page to see how it's coming along, it's a good template, and I'll be able to use this to produce the scientific documentation for the discovery.
I don't care if you subscribe. I don't care if you like. If you do either one of those things, I'm enormously gratified. But I do not want your money.
Now, Ali is going to teach us about Maxwell's field equations for electromagnetism, one of the greatest mathematical discoveries of all time. We're going to find out from Ali what are the flaws in the system. And we're going to gain some geometrical insight, which is the only insight worth coveting. Mathematical solutions are in context. There is no context now. There's nothing left except madcap adventures in mathematical manipulations that for about a century now have led absolutely nowhere. There's a saying, floats cream. And that's part of a Russian proverb that I heard when I was a teacher and a missionary in Ukraine. Ali is going to give us some guidance. Ali is a cut above. He works for the Jet Propulsion Laboratory. So did my uncle. He used to send me glossy photographs of Saturn V rockets being tested. He never sent me any pictures of the explosions, the ones that didn't work. Happily all unmanned, but we had a great deal of difficulty in beating the Russians into outer space. And this was a setup. The Russians and the Americans are exactly the same people. We have exactly the same culture, with excruciatingly minor differences. We're all white. We're all Eurasians. This man is not. Ali is descended from the stock of Abraham. The same thing will happen to you that happened to Norman Finkelstein, one of the greatest historians of our time. It's very important for you to understand the milieu of science, and I try to bring that out in each one of my videos these days. Unfortunately, it makes me emotionally elliptical. Ali al-Karaguli. Ali al-Karaguli. I'm not sure he could say it as well as I just did. He speaks perfect English. Let's listen.
And in this video, I'm going to explain to you why you probably don't understand Maxwell's equations. And even if you think you do, mathematically you think you do,
you think you do,
that you probably don't have like a deep intuitive understanding.
Probably not. He's correct.
And it's something that's very important in physics. You don't learn how to just solve a bunch of formulas and just move on. You need to actually understand the formulas. You need to understand what they're describing, and you need to feel it. It needs to be that level of understanding. So that's exactly what we're going to do in this video. So I'm going to go over these four equations.
Okay, I want to make a comment here as we get underway, and then I'll try to curtail my comments until he completes the first part of his presentation. He just made an extraordinarily profound pronouncement, which is easily brushed over yeah. We need to understand, but we also need to survive. That's a direct conflict. But he's going to show us how hard you might be able to try to get the understanding that you simply will never get, because the mathematics is incorrect, because the number system basis is wrong. That doesn't seem a very practical statement, should it be true at all. There's always something. He's trying to show us how these equations actually are. They're meant for technology.
As I usually like to do, in this case, you see there are 4 equations. This one is Gauss's law for the electric fields. This is Gauss's law for magnetic fields. This is called the Faraday law. And
don't worry about these terms.
To the people
Lori Gardy
but what you
is
need to
dead set
is how
against
they
that,
actually
so
work.
am I. You don't name things after men.
F of x equals x, where some behavior in x causes some outcome in f of x. So this left-hand side, this is a function, and this function is an outcome. It's an effect, and it's caused by a change over here. So we're going to treat everything on the right side.
I want to just make a comment on that f of x equals x. X is on one side and x is on the other, but it's transformed. This is not an equality. X does not equal f of x. So that first symbolic equation is purely an abstraction. You could say, oh yeah, you just got to adjust your mind. It's not really an equals sign equation.
Anything that's happening on the right side is going to be causing things that are happening on the left side. Now this looks like a big mess. So let's go ahead and dive into equations.
He's doing all right.
The first one, Gauss's law for electric fields, or for electrostatics, is pretty simple. It's basically showing you. And before I even explain what causes the electric field to happen, let's first talk about the del operators over here. So obviously we see here there's an E, this is a vector, this is the electric.
Look how much he's struggling. He's struggling uphill. He doesn't know where to begin. He's trying desperately. I think he's doing well, but this is a Sisyphean task. Look at the right side of the equation. What's the chicken scratch? Epsilon to the subscript 0. He's going to have a devil of a time getting around to each one of these symbols, because they're interrelated in a way that it would take him about 6 days to explain what these symbols mean back to the axiomatic basis, where I would show you where the whole fucking thing is just topsy-turvy. Let's go on and let Ali finish his lecture.
We don't care about that right now. What we're interested is understanding what the hell is this.
What the hell is this?
Upside down triangle with a dot.
And what's that
right?
dot?
So
yeah.
This upside down triangle with a dot is describing divergent behavior. So for example,
divergent behavior. Okay,
here,
that's good.
This divergent behavior is like anything that's going outwards.
This
in
is right.
Equidistant lines. So in this case, this is the divergence of the electric field, meaning the electric field is going outwards. It's going like equally in all directions.
That's a force field.
Like that. Probably look ridiculous.
That's a force
but
field.
That's basically what it's doing. So whenever you see this del with the dot next to it, this is
it's a force
divergent
field.
behavior. Alternatively, we're going to see in the later third and fourth equations, it is not a dot. It is a cross or an X. And this is called curl. This is like basically, instead of divergent behavior, this is more like rotational behavior. That's like curling around something or rotating around something. But we're going to dive into that a little bit. But it's very important that you understand this notation. So the very first one, which is Gauss's law for electric fields, it's pretty simple. It's just saying that some rho is basically charge density.
Charge density.
If I have any type of charge,
wouldn't hurt to call it that.
Like let's say whether it's, well, in this case, this is charge density. I'm going to write this in a way that's probably going to piss off some of the mathematicians and physicists. But just so you get a really deep and intuitive understanding of it, I'm going to get rid of this rho over E naught. This is the permittivity of free space.
Permittivity in free
how the
space.
behavior of the electric field is going to be shaped, whether it's in a vacuum or like
vacuum.
It's in a different material, then it's no longer, you remove the knot and you change it based on the material. I'm going to get rid of all that confusing nonsense if this is the first time you're being introduced to this. I'm just going to put like a squiggle here that says this is sort of equal to Q, which is charge.
Boy.
Now obviously charge is related to charge density because at the end of the day, charge.
Yeah, what's charge density? What
is just how much charge
density
is flowing
in
over
what?
a certain area. So I'm just basically going to replace
That's
the rho
incorrect.
with a Q, and I'm going to add the squiggle. If you have some type of charge, and especially like an accumulation of charges over like
How
a
do we
certain,
know that's plus
surface or a
minus?
certain volume.
Is that correct?
In this case, that's what the rho is.
No.
That charge is going to create an electric field. That charge is going to create some type of electric field, which is basically
an
a
electric field
in which there is a force to be felt.
force.
Right?
That's
At the end of the day, the electric
incredibly
field is
important.
just
It's
wherever
a
you
force.
exist within that electric field. Obviously, the closer
So
you
a
are to the
field
source,
is a
the stronger
force.
you feel it.
That's
But you're
correct.
going to feel some type of pull, or push. You're going to feel some type of force. That's exerted
There
by
are
this
only
electric
two
field.
of those forces
So all
in
this
the
very
whole
first law,
universe.
Gauss's law
He
is telling
doesn't
us
know
In
that.
order to generate an electric field, the effect, you need a cause, which is rho, charge density, right? And then obviously, because of the E naught,
Whatever any of this means,
permittivity,
no meaning
this is
yet.
also a signal that
Zero
the electric field's
meaning.
behavior is going to depend
But
on
this
what
is
material
important.
you are in it. So I'm going to rewrite this to be the correct form, which is rho.
You know what's
over E
missing?
naught. So basically, these
Geometry.
two variables. Well,
He
this one
doesn't
is
know
usually a constant,
geometry.
but if the material's changing, then
He's
it becomes a variable.
untrained in
These two
geometry. They
over
all
here,
are
the
untrained
rho
in
and the
geometry.
E naught,
They
are
never
basically gonna
even
determine
mention
what
that
kind of
word
electric field
unless it's to
you're gonna
deceive
have.
you.
But we know for sure it's going to have divergent behavior, right? Because it's coming as a result of the charge.
What that
the
means
charge
is
density.
an outward
Okay?
pressure
Now, if we take this
spherically.
same
He
concept
doesn't know that.
and take a look at the second equation, which basically says the exact same thing, except we're going to replace the E with the B. And
That's
we're going to keep this
magnetism.
divergent behavior. We're going to realize that this is actually
Contractual, although that's
equal to
weird.
zero.
Zero.
And you might be
There's
confused,
your
you're like,
lucky
what
number.
What does it mean if it's equals to zero?
Means
well,
nothing.
That means if you want a divergent
This
magnetic
means
field, if you want a
nothing, is
magnetic
what that
field
equation
behaves
says.
Like this,
Anything
that
related to
diverges and
zero
that doesn't curl,
is shit.
It's going to be caused by nothing. Nothing can cause that.
Nothing
it's
can
impossible.
cause
At least
that.
to
It's
our
impossible.
understanding, based on physics, there are no such things as like magnetic charges or magnetic
No
monopoles.
such thing
There's
as-
no single thing that creates a magnetic field.
Oh, well,
We're going to
that's
see
true.
from the other
There's no
equations later
single
on that a
thing,
magnetic
that's
field
right.
has to be caused by
So what are the
something
two
else,
things that
which
cause
hence
this?
It's the electric field.
He has no
And you can
idea.
actually realize that the electric
He's
magnetic
dancing
field is just
around
kind
a
of like
maypole.
a different kind of electric
Dancing
field.
around
And
a
they're kind of
magic
the same
fire.
thing, a little bit. So
He's hoping-
we know that from equation 2, which again this is Gauss's
I
law
don't
for
know.
magnetic fields,
These
is that
poor
if you
men,
want
I
to
really
see
pity
divergent
these
behavior in
people to
magnetism, guess what?
explain
You're never
this
going to see
shit.
it because there is no magnetic monopole, there is no magnetic charge. So again, to see how these guys compare to
You
each other.
following this? Because I've already watched it and it's still.
This is going to be equal to rho.
He's struggling
You
so
know, and this is
hard.
gonna
He's
equal to zero.
desperate.
So if you want to have a divergent electric field, or an electrostatic field in this case, well, you just need a bunch of charges that are chilling, in this case, in free space. And if you're trying to have a divergent magnetic field, well, you're never going to find it because magnetic fields cannot be created on their own. Which brings us to the third and fourth Maxwell's equations laws. So we're going to start with equation number 3, which is called Faraday's law. And it's pretty simple. It's basically telling you that the curl of the electric field, in other words, the rotational behavior or the electric field doing this compared to like divergence, which is like doing that, is caused by something. And it's caused by something pretty straightforward, which is simply a changing magnetic field, right? And again, we want to look at this equal sign, where this right side is the cause, this is the effect. And it's telling you, if you have a magnetic field that is changing with respect to time, in other words, if you take a magnetic field's strength and you see that it's changing with respect to time, and you can even graph it, it would probably look something like this. Like, let's say this is magnetic field strength, this is time, and the magnetic field is varying. You take the derivative of this guy, you take the rate at which this magnetic field is changing with respect to this time, and that derivative is actually going to tell you the curl of the electric field. It's going to tell you that there's an electric field being induced at this rate. And this is something that's very, very powerful. This was discovered by Michael Faraday, and he was actually originally a chemist. He wasn't even a physicist, and he was an experimentalist. He was a
is in the
hands-on
duality.
tinkerer type of
That's
guy. And he was
geometric.
just like running a bunch of experiments in his lab. And you notice that if you're changing the magnetic field, if you're passing some type of magnetic material, well, then you're able to induce an electric field. You're able to see an electric current as a result of that. And this is something that's actually very, very important. I want to pause here and make an extremely important point, is that some of the greatest physicists in history, they're not just people who are like doing math all day. Like, there's this perception of physics that in the movies and whatnot, that like physicists are just like doing crazy equations all the time. But like the truly great physicists, such as James Clerk Maxwell, such as Michael Faraday, such as Albert Einstein, their advantage is that they had such a deep, intuitive, and visual understanding of what's going on. They were just
geometric,
such observational people.
That's true.
And Michael Faraday wasn't even that good at math. He had
you don't have
I think
to
algebra
be.
was like his
The only
strongest,
time you need
like,
math
he didn't
is
know
for your
more
proof.
than like what people would consider high
And
school
then
math.
God help you,
But
because
what he
the
was very
mathematics
good at
system is a
he was
shambles.
a very good scientist. He was very good at practicing the scientific method. He was very good at coming up with an idea, running the experiment and observing what happens, and then saying, oh, that's weird, why did that happen? And then just like thinking about it, trying to understand what it is. So if you're someone who's interested in engineering, math, or physics, it is very important that you actually try to understand.
Understand, he means visualize.
And
visualize,
not just, like,
geometrically.
And, like,
that's understanding. That's the definition of understanding in science.
Anyway, a little bit of a tangent.
Visualization through geometry.
We all have a job to
Not
do. You make Riley happy. Sadness makes her
Not
sad.
mathematics.
Fear protects her from the scary stuff she can see.
Not mathematics. That little animated character probably knows more about physics than the professor does. See that? Look at that. They're using their brains. All right, let's go on.
The fourth equation, which is called the Ampere-Maxwell law.
You do have to use your brain.
And it goes like this. Again, we have this
Not
little
easy.
operator with
It's
the
not easy to
X.
use your
This is a
brain.
curl.
None of your
And
mathematicians
this is basically
do.
telling you that
They
again,
use
some type of
mathematics.
rotational
That's
curling behavior in
surrogate
magnetic field. If you want
intelligence.
to induce a magnetic field that is rotating, and again, not divergent, because we discussed that you cannot have a divergent magnetic field, and that is going to be caused by two things, right? And there's two people to give credit for this for. Very first one was Ampere. So this is called the Ampere law, where it's telling you that if you have some type of J current density, basically an accumulation of charges that are varying, that are moving, and hence we measure current in the unit of amps. It's in credit of ampere. That's going to create a magnetic field, and you can try that. If you're passing current through a wire, you're going to create a magnetic field. You can detect that there is a magnetic field. But then there's another way you change an electric field. And in this case, obviously, we have the permeability depending on what material you are. Is that this is just dE over dt. So, I don't know if you guys can see that. Yeah, I think you guys can see that.
I do.
So over here we have two things again, this is a plus. Plus meaning these things are not depending on each other. You can think of this as like an OR gate, where like if you have current, cool, that's gonna change your magnetic field. Or if you have changing electric field, cool, that's gonna change your magnetic field. But they don't depend on each other. You need one or the other. So basically Ampere made this observation, and then Maxwell made the observation of, no, actually when you change an electric field, then you can induce a magnetic field as well. So now we know that in order for you to induce a magnetic field, you can do that either by varying an electric field, or you can do it by passing electric current through a wire. And that's pretty much it. Now here's the cool part, is if you take this equation, and the one we just looked at before, and by the way, these are obviously vector fields, and here we...
You hear him try to gasp for breath there?
We have just a minus
He is in misery right now.
dV over dt.
Look at that. Oh my
If you
God.
take these two equations, there's a way that you can combine them together, and what you would derive is you would derive the wave equation. And this is how electromagnetic waves are formed. For example, the light that's hitting me right now, from all over these lights, or the one bouncing off the board and hitting me, or the one hitting your eyes right now, it is traveling through the form of electromagnetic waves. There's an electric field that's like doing this, and then in parallel to it, there's a magnetic field that's like also oscillating with respect to it.
That is not parallel.
And the changing electric field induces a magnetic field. The magnetic
That
field
is
is
not
changing, so it induces an electric
parallelity.
field, and they just do this dance infinitesimally. And if you take like the derivative of, like, for example, if you take sine, if you try to
other
take the
words,
derivative of
it's
sine or cosine, and you just keep doing that back and forth, you will notice that all you
Sine
end up
and
doing is
cosine,
you're just
those are
getting
derivatives.
oscillating behavior.
They're not
now,
rational.
I can make a separate video
So
about
this
this
does
if
not
you want me
work.
to talk a bit further about the wave equation or waves in general, or how you can go from Maxwell's equations to understanding waves. Then you can leave a comment and let me know below. But that's pretty much it.
Yeah,
If you like this video,
that's
you can leave a
pretty
like
much it.
and let me know what you liked. If you did not like it, then you can leave a dislike and write.
Okay, I hope you enjoyed that. It's quite difficult to follow. He's not alone in this. He's a good presenter. I don't really find fault with him, except to the necessary extent that there is nobody from Dr. Leonard Susskind of Stanford to any of the other presenters, either on YouTube or on the university circuit or anywhere else, who write books. They cannot explain Maxwell's equations because they're inexplicable. You saw the zero, and you noticed that Ali was talking about the electric field and magnetic field propagating through space in parallel. You could say that because that's an electrical engineering point of view, because they're concerned with pressure, the pressure of electrical force through a wire or a circuit. That's all they're interested in, because that gives power. Power for our computers, as Ali carefully described. They also mentioned the propagation of light through free space, that the two fields are perpendicular. It seems that they travel through space in parallel because that's the line of motion. Since they're both propagating in the same line of motion, you could say they're parallel. But that completely overlooks what's really happening. I hope that you gain some insight from this rather provocative statement that I'm making here, that the two forces are perpendicular, not parallel. But in what space are they perpendicular? Because they're traveling through space. So how are they perpendicular? Our interpretation of such basic equations as the Einstein field equation, the Einstein energy equation, Max Planck's formulation of the frequency wavelength relationship as interpreted as light speed, and we need to get right down to how science is, that is physics, is attempting to explain the universe. But that's 40 minutes, that's the maximum for an American audience, as I've learned. It's already 4 times the amount that most Americans are able to digest. So thank you very much for tuning in. I really appreciate my viewership. I now have 144 subscribers. This was unforeseeable to me 3 years ago when I began. So I'm now entering the final phase to deliver, as I must according to my vows to the universe. The pact that the universe and I entered into when I became a scientist. This is the definition of a true scientist, which I claim to be and now will prove. That you're seeking information and understanding directly from the universe. That means that you cannot use mathematics unless you use the applicable mathematics. And there are 2 systems of mathematics. I discovered that. So I'll be teaching you the basics of cosmic arithmetic over and over and over again till I drop dead. But without this paper, it can never enter into consensual science. So I have to go into the arena, which I loathe, because I'm combative, and I have to be. And this has been one of the biggest struggles that I've had to face. I did not ever foresee that I would make a discovery when I began. So the paper will be out within 2 weeks in its prototypical form so you can review it. And my name is Euclides. AE. This is Anagalactic, bringing you the secrets of the universe. Don't forget to keep looking up. It's a little difficult here in Chico since it's raining. We thank our Creator for the rain that comes on a cycle. So keep looking up. Don't ever take your eyes off the universe. That's your teacher. I am just a prophet.